So now we have Ron, who's going to give a very interesting talk. I'm very intrigued about this, about a really neat bug in the LaunchServices subsystem. So let's give Ron a round of applause.
All right. Hey, everyone. Thanks for coming. I'm Ron. I do product security at Okta. That's me. And today we're going to be talking about a fun little bug in LaunchServices that let an attacker escape the App Sandbox in multiple different ways. Because we're talking about the App Sandbox, we are going to give you a bit of a refresher on its restrictions, what it is, how it works. Then we're also going to give you some context for the bug by way of reversing the relevant structures and flows. And then we're going to get into the guts of the presentation where we're going to exploit this one issue in 5 different ways. Afterwards, we're going to speak a little bit about how Apple decided to patch this, and also give you some idea about variants that will invariably crop up. And then finally, just to be responsible, we're going to be, we're going to be talking about how you can defend yourself via tools and heuristics. So let's get into it. So the App Sandbox. The App Sandbox is a security measure that's designed to mitigate damage in 2 main situations, either of which have to do with the Mac App Store. So the first of which is a user installing a malicious app from the Mac App Store, and the second is an app becoming compromised after the fact. So you can see there in the little graphic of Apple's, credit to them, that without the sandbox, an app otherwise has unfettered access to user data and system resources. Note, of course, with privacy protections, there's a bit more nuance to that. And with the App Sandbox, you're kind of confined to your little sandlot that's allocated for your app. One other thing I want to mention, and it'll come up later, is Office macros run in the App Sandbox. Now let's get into it further. So concretely, you're allowed to access the file system in your container under tilde library containers followed by your bundle identifier. You're allowed communication with a limited set of mock services. You're allowed to start processes with a POSIX spawn, fork, exec, ns task, but the caveat here being that child processes will inherit the App Sandbox and thus all of its restrictions. So you can't just execute something and that's an escape. Now, the one thing, it's not so much a secret as it is not really talked about. It's the ability to start processes through LaunchServices, which is what we're going to focus on today. If you want to find a fullish list of exceptions on what you're allowed to do in the application sandbox, there's the seatbelt profile. It just defines restrictions. OK, so App Sandbox and LaunchServices. Ostensibly, this capability is intended for launching helper apps, which are just apps inside your app. At least that's the only mention of it in the App Sandbox guide. And as you might intuit already, LaunchServices is responsible for launching applications, opening files. That's what it does. It's explicitly allowed in the seatbelt profile via these 2 lines, the first of which is a mock lookup on the quarantine resolver service, and the second of which is ls open. The XPC service is implemented in the core services UI agent, which already had a feature in the last presentation. So let's take a closer look at that. Side note, this agent does a lot of stuff. The service is called Quarantine Resolver. It does stuff related to that. It shows prompts. It's, many tricks. Scott Knight has a great post, which I linked to. He reverses all the various message handlers, but the one we're going to talk about today is the CS UI ls open handler. And this one essentially just acts as a LaunchD proxy. So how it works when your sandbox app calls into an API like OpenURL, OpenURL is going to call into LaunchServices, it's going to put together the required data, and it's going to send it over to the core services UI agent. Then the core services UI agent is going to put together an RBS launch request and send that to running board D, which is new in Big Sur. Before, it would go directly to just LaunchD. But now running board D is going to submit that LaunchD job, and LaunchD will finally launch the specified application. Now, 2 things I want to highlight here before we go forward. The first is that you can launch another app from within the App Sandbox, but you can't provide it any arguments. You can't pass any sort of input to it. You could just launch it. It'll just be there. And the second of which, unlike an API like POSIX spawn, when you launch an app this way, it's not going to inherit the App Sandbox. So that's a really interesting one to look at if our goal here is to escape. OK, so let's take a closer look at the input provided. It's a serialized ls remote OpenCall structure. I've picked apart the relevant bits here. You can see it has an IVAR called inputs. Inputs looks like this. It takes an NS array of in URLs to open, as well as in-app params. In-app params has the following structure. There's an NS dictionary called environment. Hint, hint, wink, wink. This is connected to the title of the presentation, and an NS URL called application URL. A quick side note on sort of how I recover these structures. If anybody's taken a look at the DYLD shared cache in Big Sur, you probably noticed a lot of authenticated pointers and unparsed addresses, and class dump just, craps its pants. And the assembly all around just looks very ugly. So I wrote a little Hopper plugin that glues together class dump and some private APIs and recovers something like a human readable representation. Essentially, you could start reading the code again. So that's open source. You could use it if you'd like. All right, now let's go back to that input. This time, the relevant part is gonna be highlighted. And let's take a step back. So I mentioned that in the App Sandbox, you can launch another app, but you can't pass any arguments to it. There's no arguments IVAR or anything like that. So what is the environment IVAR doing there? I find that especially weird. I don't know about you. And I mean, I assume that okay, maybe that would just be ignored later down the stack, later on down the line, but it isn't. And that's the root cause of the bug we're gonna be talking about today. That a sandboxed application can launch other applications outside of the sandbox and control their environment variables. Now, this is a really interesting primitive, and at first I wasn't sure if this was exploitable. I assumed, oh, Apple clearly had thought of this, but I'll show you in just a sec. So, triggered this the hard way. It's not really that hard, but you'll see why I'm going this hard relative to the other stuff. You extract the relevant structures, say through class dump, DSC tool, whatever you will, write your XPC client, set that environment IVAR to the environment variables of your choice, so just an NS dictionary. In this case, we set food to bar. And then go ahead and send it to the quarantine resolver service. The core services UI agent is going to launch the app outside of the sandbox, and it's going to have a controlled environment. But it gets even easier, and you could just use the API. In this case, if we instantiate NS Workspace Open Configuration, we set the environment property to that same NS dictionary, food to bar. We'll pass that to OpenURL, and it's going to launch Safari with a controlled environment. Surely Apple couldn't have overlooked that, right? And if you go take a look at the documentation, you'll see this case is explicitly called out. It says, if the calling process is sandboxed, the system ignores the value of this property. Now, we're about 10 months since I first reported this issue, and the 4 subsequent reports, I keep calling the documentation out as, this is the expected behavior. The observed behavior is that the system does not ignore the value of this property, and it remains. One potential explanation for why this is a new feature in Big Sur, and that's the inheritance of environment variables through LaunchServices. So here I have a little snippet of pseudocode into how this is implemented. Essentially, a LaunchServices client that wants to launch another app, it's going to collect the environment in the client and then try and set that in the launched application. Pretty straightforward to mimic, ordinary process execution behavior, but there's one thing here. It also does some sandbox checking. You can see it checks that if the client is sandboxed and it has the variables home, tempdir, or cffixed user home set, it's going to continue. It's going to ignore them. But I've said the magic word already, and that's precisely the problem with this, and that this is client-side validation. And we'll abuse this in just a moment. Okay, now let's get into the actual fun stuff. So initial report, we can control environment variables. My first thought was DYLD insert libraries. Hell yeah, let's point this to a dilib of our choice and then just load that outside the sandbox. Easy peasy. For those that don't know, this is similar to like LD preload. You just point this to a pass to a dilib, and that should be loaded when DYLD and the process start. But we have one major restriction, and that's in Apple Mobile File Integrity, there's a policy that makes DYLD variables ignored on Apple binaries. So you can't just set this environment variable on something like photos and then launch it and then have a good fun time. It's not gonna work like that. Instead, I found another target. It's a script editor template called Cocoa Applet. It's available on default installations of macOS, so we don't have to deal with anything like a quarantine X attribute. It's unsigned, so it's not technically an Apple binary, but most importantly, it's the perfect host app for the exploit because it runs outside the sandbox. So this is relatively straightforward. How it's going to look is something like this. I hope the graphic is big enough. We're just going to point DYLD insert libraries to a bundled dilib inside of our application. Remember, this is from the perspective, at least in this case, of like a malicious Mac App Store app. We're going to put it under frameworks like many libraries are. Nothing too special there. We're going to launch Cocoa Applet through the front door, through LaunchServices. Once again, nothing out of the ordinary. And then Cocoa Applet is going to load with our set environment variable, and DYLD is going to load the dilib outside of the sandbox. Okay, I was so proud of myself. I thought this was amazing. And then I went and I tried it on Big Sur. And then Big Sur the first issue I ran into was new signing and notarization requirements on ARM64 binaries. But that's easy enough to bypass. You could just change the architecture in the launch request. But then another thing I noticed was that Cocoa Applet popped the first launch prompt. It said, "Are you sure you want to open Cocoa Applet?" We didn't sign it. And then I was like, damn, because what that made it was requiring user interaction. So now we know the user is going to click through the prompt anyway, but ideally there's no prompt at all in the first place. So kind of lousy, but Apple thought, like, fine, we'll fix it. It's weird behavior. They patched it in 11.4. They now check if a variable you want to set has DYLD prefix, and if it does, it's just ignored. It's not sent along in the launch request. And that's what the input looks like in the console. Water break. Okay, so let's go back to that requirement. There's interaction requirement. I mean, there's an interaction requirement here in this exploit, and that makes it sort of lousy. Let's get rid of it properly. And we're going to do that through this very funky environment variable. And there are two parts here. Let's break it apart. So the first part, the _XPC prefix. If you set an environment variable prefix with _XPC on an app, and that app launches an XPC service, libxpc is going to strip the prefix and set the rest of the variable on the started service. So this is a way to set an arbitrary environment variable on the service of an app. And now the second part. Our target for this one is going to be music.app, which has a service called Visualizer Service, and Visualizer Service loads plugins from tilde, library, iTunes plugins. Now, how is this URI resolved? It's built with NS search path from directories and domains. The second argument is passed NS user domain mask. And when that argument is passed, it's going to call into NS home directory to expand the tilde. And NS home directory has a fast path where it just reads the value of cfx user home. Now this might all start coming together. Here's the flow. Let's go over it. And our goal here is to load a malicious plugin once again within our app. Here's how it's going to work. So step number one, we're going to set XPC cfix user home to our App Sandbox container. We have rewrite access within the container. In that folder, we can start to recreate the directory structure that the service expects. And we'll do that, but one last part. In creating that directory structure, we're going to symlink app resources to iTunes plugins so that we don't have to copy the plugin from inside the app to the container, because that's going to add the quarantine X attribute to it, and it's going to fail to load, essentially. So we do this symlink trick to build a directory structure, have this plugin available, and then we're just going to, once again, launch it through the front door. We're going to launch music.app. Music.app is going to start its XPC service, Visualizer Service, through XPC connection create, at which point libxpc is going to strip the prefix, set cfixed user home on that service, and then when the service tries to resolve the URI, it's going to point to inside the container, at which point the symlink is going to be traversed, and that's going to point to inside the app. And then this time, we properly have a no interaction sandbox escape. Okay, but still something's nagging me. And that's the requirement to bundle something with the app. You know, I figure, like, if I put something in my app and it's an iTunes plugin, I would really hope that App Store review would probably have some sort of heuristic and flag that, or, you know, trigger manual review or something. So can we remove that requirement, the one where we have to bundle something inside it? And we're going to do that through home. So remember I mentioned that Big Sur feature? There was some validation done of home tempdir cfixed user home, and I mentioned it was done client side. It's time to bypass. So we're just going to send the data directly to the service. We're just going to go around LaunchServices framework and send it directly to the endpoint. And our target for this one is going to be terminal.app. Here's the flow. Let's step through it and understand how this works. So step number one, we're going to write out a malicious.profile in our sandboxes container. We can do this because we have read-write access, and in .profile, there's going to be arbitrary shell commands. It's going to be the jump-off point for our second stage or whatever we want. Then we're going to build the dictionary and then set it in the environment ivar. We're going to point home to the sandboxes container, and then we're going to send the XPC message directly to the service. Going to bypass that LaunchServices client-side validation. Home will not be ignored, and then when launchd launches terminal.app outside of the sandbox, terminal.app will in turn launch a login shell with that controlled value of home, and the login shell is going to execute home/.profile. I think a bit of an improvement over the last one. So This was patched recently in 11.6 as a silent patch. I asked Apple why I wasn't credited, and then I'm sort of being gaslighted. They're telling me it was fixed in 11.5, even though 11.5 was the tested vulnerable version in my initial report. But anyways, yeah. So they check to see if the variable you want to set is home, and if it is, they overwrite that value with the value in the core services agent, which cannot be tampered with, at least from within the App Sandbox. And they also check if the variable you want to set has the XPC prefix or is equal to cffix user home. And similar to the last patch, they're going to ignore the variable and not send it along in the launch request. Okay, now let's quickly sum up what we have so far. We have an interaction required exploit. We'll forget about that. That sucks. We have one where we have to bundle something inside the app. Not so good. We have a better one, which I just showed you how we can do it at runtime. We can write out a file and then have that executed. But can we remove that requirement? Can we avoid writing to disk and make this properly fileless? We can. So let's take a look first at this API, NS Workspace Open URL. Pretty intuitive. It just opens the URL you pass to it. What it does under the hood is it's going to take that argument and set in URLs to that argument in the OpenCall input structure I mentioned earlier. The structure itself doesn't matter. Now, what if we passed not an app, not a bundle, but a Unix executable? What if we passed Perl? And you'd see a prompt like this if you tried to do that. What would happen is the UTI of Perl would be evaluated to public.unix executable, and then the binding for Unix executable would be evaluated to see that terminal has registered to open it, and then some checks there are going to prevent that from happening. Now, what if we look at its ugly deprecated cousin, launch application? So what happens here is it takes that argument and it sets application URL in the application parameters structure. This time, passing Perl is going to bypass that check. And before I get into the exploit, a lot of you already know that we've just tremendously expanded our attack surface. A lot of Unix executables, I don't know, people used to love shoving features into environment variables. User bin Perl was chosen particularly for a very special one. So I call this one MOAB, mother of all bypasses. I'm not even going to show you a flow because it's so simple. Let's step through it. So number one, note that we're using setenv. We're using setenv to abuse the Big Sur inheritance feature, and here's what we're doing. We're first going to set Perl 5 op to -d. This is going to run Perl in debug mode, and when Perl is running in debug mode, it's going to take the value of Perl 5 db, and it's going to prepend that to any code you want to execute. So essentially, it's Perl code in an environment variable. This is perfect. And then we'll bypass the core services restrictions for Perl by calling into the deprecated API. And this is properly fileless, silent, zero interaction, and I think as a cherry on top is probably tweetable. So in 3 lines, there are 3 issues. The first of which, environment variable inheritance between sandbox and unsandbox contexts. I think, when we first started and we saw that IVAR, we were wondering what it was doing there, but I think at this point we've properly demonstrated that this is crossing some sort of privilege boundary. Next, we bypass restrictions for Unix executable by calling into a deprecated API. Clearly, it's a code path where it's missing the same checks as the supported one. And then finally, it's not so much an issue as it is Perl's command injection as a feature, Perl 5 db, it's awesome, sweet. So the third patch here, it was issued in 11.5. What it does is it checks to see that the argument you pass to the APIs or the core services agent, if it's a registered bundle, okay, cool, but if it isn't and you're sandboxed, then it throws a permission error. Last exploit for today has to do with Electron. And Electron is the darling of macOS red teams. I know the entire Zoom red team is here, so I think they'll like this one. It's a known process injection vector when you just set Electron run as node. You can pass your arbitrary JavaScript through argv, through standard input, and you can execute it in the context of the application. Doing so subverts the entire macOS security model, and you can abuse the TCC privileges and entitlements of the app. But we can't just use it as is from the App Sandbox because, once again, we can't specify the arguments to the app we launch. However, we do have a very strong primitive available to us, and that's controlled environment. And we can achieve process injection through node options, where you can pass command line flags to the underlying node process in an Electron app. And the one we're interested in is the require flag, where it takes the script provided and it just executes it. That's it. Now, there's a bit of nuance to this, because officially, according to Electron docs, this is only for unpackaged apps. For packaged apps, it's filtered. A packaged Electron app has its main executable renamed from Electron, all right? But there was some Unicode parsing bug where it wasn't properly filtered. They sort of fixed it. They were going to fix it only for Windows. I pointed out, hey, this affects all platforms. Then they properly kind of fixed it. They didn't issue a security advisory while also acknowledging its security-related nature. Then I reported another patch bypass to them where you just pass Electron run as node alongside node options, and node options will not be filtered on packaged apps, clearly in contradiction to their docs. And then finally, after months of ignoring me, they say, we do not consider physically local attacks in our threat model, citing Chromium or something. While once again, also elsewhere, contradicting themselves, saying require will remain filtered in upstream Electron as a security measure. So now we're in a sort of pickle, because this is a third-party vector, which means Apple probably doesn't care about it. And the third-party framework, in this case, also doesn't care about it. So I think it's up to sort of the community, the users, to work around this themselves and understand how this can be exploited. And this can be exploited even simpler than the other ones, I believe. So let me just go over the two lines that are occurring here. First, we cat a head document to payload.js. This is going to be the code we execute outside of the sandbox in the context of the Electron app. We're just going to touch a file under applications, which you normally can't do from within the sandbox. And then we're going to trigger the issue we talked about today in the third way, the easiest way yet. And that's the OpenCLI binary, which is going to call into LaunchServices. Even better, we can populate that environment IVAR through the N flag, where we set Electron run as node to 1 to bypass the node options filtering, and then in node options will require the file we just wrote. And that's it. We have both a macro sandbox escape and process injection in 2 lines. And nobody wants to fix this. What the heck? So workaround here, if you are responsible for an Electron app, package your app. Make sure it's not named Electron, like VS Code and Keybase. And also disable the run as node fuse. This is a sort of experimental, not really documented feature, but it essentially makes your app ignore the value of Electron run as node. This should never be enabled. Now, what's left? Clearly, Apple has chosen a whack-a-mole approach. Instead of addressing the root cause of the issue like their docs explicitly state, they're patching things as I find new vectors, as I report them. What gives? The crux of the issue remains, and that's that applications can still be launched outside of the sandbox, and their environment variables can still be controlled. I think a big thing we'll see here, certainly see, I have one thing in disclosure right now, is application-specific environment variables. Today's example was node options, but there are more. I've also shown you APIs influenced by environment variables. Today's example is CF fixed user home and NS home directory, and the many APIs that expand tildes and paths through that API. And also, sandbox parameters are sometimes initialized by environment variables. The example I have is the Trusted Peers Helper service, where the home subpath is initialized from the home environment variable as opposed to somewhere more secure like Open Directory D. Yeah. Now, if you want to defend yourself, I've submitted a PR to the Objective-C process monitor tool. It's not merged yet, but we'll get there, right, Patrick? And what you want to look for is essentially everything we talked about today. If you see an unsandboxed app with its value of CF fixed user home containing containers, in other words, it's pointing to a sandbox container, but it's not sandboxed, that's very suspicious. Chaba Fitzel's Shield app also looks for Electron run as node, but not the latter, node option. So if it's an unpackaged app, yeah, you'll need something else for that. And another heuristic, one final one, if you can determine that a process was launched through LaunchServices, and then you could also obtain the parent PID of that process, the one who submitted it, check Jaron Bradley's TrueTree project for that. If the parent is sandboxed and the child process is unsandboxed, that should probably add some weight to your detection algorithm. And I think I'm just about out of time, so mahalo to Andy and Patrick, and thank you to Matthias and Juan and Okta for supporting me. Thank you, everyone.